All right, so now that you've seen how easy it is to evade these classification tasks and fool the model, then you wonder, what is the defense? And there is a defense called deep neural rejection, which is, by the way, very easy to understand intuitively. You could look at those images and see they're messed up. They have that snow in them. The other ones don't have that snow in them. So that's all you have to do. So what you do is you train a whole model, and then you add a few more parameters. You measure some parameters of the images and measure the distribution of them, and then you combine those into some measure of the shape of the image, and then you throw away the ones that are outliers. This is a very simple task. Classify them and throw away the ones that are like 1% away, 1% that are furthest from the others. That turns out to work. So here, you get the images. It's again these handwritten digits we're trying to categorize. You train your model, and your model is pretty good, and you can see how often it is correct. And here's the actual output, by the way. The image number 0 is a 7, and it's predicted to be a 7. Here's the output of the model for each parameter, and see 7 is 5005. All the others are negative or small, like 270, so the largest signal is the one we call right. And this is what I mentioned before. The actual model produces an analog output. It doesn't give you a categorization, yes or no, and you then have a threshold where you decide above a certain point. In this case, it just takes the largest analog output, and that's the prediction. So now we can attack the unprotected model. We're going to make some attack images, and here they are. The attack image is like before with some extra snow in them. And now, look how wrong it is. It thinks this is a 0. It thinks this is a 0. It thinks this is an 8. It thinks that is an 8. You know, the poisoning is very effective. Those little bits of snow completely foul up the model. So now, here's the correct and predicted number of successful evasions, 20 out of 20. By the way, I'm not much of a researcher. I'm not doing anything deep anymore. Most of these are just following online tutorials. As mentioned, this is my only contribution to the field. This was a research paper. It took me a week to write this project because the original research paper proved that their defense was working with some complicated mathematical charts that I could not understand at all. And I said, there's got to be a simpler way to show that it's working. So this was my huge invention. Just see how much it'll fool these 20 evasive images. Now you train your deep neural rejection, which measures parameters and throws away the outliers. Now, in addition to calculating a prediction between 0 and 9, it's allowed to say, I refuse to use this image. This image looks funny. That's going to be a -1. And now, after you train that deep neural rejector, that's what it does. There's an R here. It rejects some of the images. So you prepare attack images for it, and now you'll see -1 means, I know this image looks funny, I'm not going to categorize it. So the end result is now you only have 6 successful evasions instead of 20. The rest, it correctly identified as obviously evil images. These images have been poisoned. These images are trying to fool me. I'm not going to take them. So that's the defense. That's one of the defenses we have so far. And you can play a lot of games here and get a lot of flags showing various versions of this. So